So in this video, we'll introduce a new topic about the determinant. And the property of determinants is so important. It's probably one of the most important concepts during the whole course linear algebra. And please look at the notation here. In this video, we only talk about the easier case, which is the smallest square matrix 2 by 2. And the notation for determinant is like this. And just to let you know, determinant is a complicated formula for us to find a real number associated to any square matrix. But specifically, let's look at how the formula like for a 2 by 2 matrix. And I will write down the general steps. Then you'll see in the next video, all these steps actually can be applied successfully also for the higher square matrix. So the first building block to the fairly complicated formula is the part A, which is something called the minor. And minor corresponds to the position on the matrix you would like to talk about. Of course, now the matrix is small, but the concept of minor, for example, depends on the row and column you choose. So basically, for each spot, there's one minor, right? For example, for this spot, it's going to be the big M subscript 1, 2. And for this spot, it's going to be the big M 2, 1. This one is the big M 2, 2. And the definition of minor is it is actually the remaining number after deleting the ith row and the jth column. And to illustrate this concept, let's look at a concrete example. So let's give you the 2 by 2 matrix like this, you see. And for example, to find the minor at the position which is on the first row and the first column, this number is going to be the remaining number after deleting the first row and the first column, right? After deleting this, so you see it's a 2 by 2 matrix. So you're left with only one number, which is 4 now, right? And let's do the remaining calculation for the minors. For example, for the minor on this position, which is this, which is the first row and the second column, you have to delete the first row and the second column. So you're left with only one number. On the bottom left, it's going to be 3. And similarly, I write down the remaining minor here. So the number is going to be like this. Please look at how we delete the rows and columns. Depends on the position you look at. And that's the way to find the minor. And the second building block to find the determinant is what we call the checkerboard of a matrix. Basically, you have to put in a sign. And we usually start with the top left. It's going to be positive. And the remaining entries must have the opposite sign to the neighbors. So it means what? It means the next entry, it must be minus minus like this, and this one is plus. So for example, just a simple example for you, and of course the checkerboard applies to any matrix regardless of their size. And the building block C is about finding the determinant by our method. We call it a cofactor expansion. So I'd like to make the note that the determinant formula does not depend on the row or the column you choose for the cofactor expansion. And let's do the first one for the cofactor expansion on the first row. You see the first row means you should have two terms like this, and the first term is the product of the matrix entry with the minor at that position, and similarly for the second term. And let's do this calculation together. So you see the minor is obtained by deleting the first row and the first column. So you get 2 here. And for the minor here, you have to delete the first row and the second column, right? So you're left with the bottom left number. So it's going to be the determinant minus 1 in this case. And we'll do other cofactor expansion now. So let's try to do the cofactor expansion on the first column. So you have two terms like this. So there should be two terms, plus and minus. Once again, the first term is the position 1, 1, which is the product of the matrix entry with its minor on the same position. And the second term is going to be the position 2, 1, right? And let's do this calculation together. You see the minor at this position is going to be the number which is in the bottom right, and this number is going to be the number remaining after deleting the second row and the first column is going to be 3, right? And you see now the determinant is minus 1, which is the same as the answer you obtained cofactor expansion on the row 1, right? So it gives you a sense that cofactor expansion never change, even if you choose others. For example, you can choose row 2, you can choose column 2. You will obtain the answer minus 1 at the end. So that's the way to find the determinant of a 2 by 2 matrix. So you actually write the matrix 2 by 2 in terms of A, B, C, D. You would notice that the determinant, if we try to do it by the cofactor expansion on the row 1, will obtain such a formula. This one is the minor at the position 1, 1, and this one is the minor at the position 1, 2. So this number is C and the remaining number is actually D, which means the determinant formula is actually AD minus BC. And if you recall, you can actually recall the inverse formula for the 2 by 2 matrix. We have presented it a few videos earlier. Please recall this term is exactly the same as our determinant formula here. It is not a coincidence. I would like to emphasize the fact is that the theory behind the determinant is intimately related to how you find the inverse actually, and it covers lots of theoretical properties of matrices also. But because of this fact, we can actually write the inverse formula for 2 by 2 matrix by something like that, right? Now you see, can you connect all the concepts together? Can you tell me under what condition for the determinant of M will get an invertible matrix M? I for this formula to be well defined, the fact is that the denominator in the scalar should be non-zero, right? So you see, it essentially means that when the determinant is non-zero, the M inverse exists. Or the other way to say is that M is actually invertible.